Hi everyone, and welcome to Erik's Electronics Workbench and part 2 of the ADCOM GFP-1A audio preamplifier service and restoration. Now if you haven't seen the part 1 video, make sure to check that out. I'll post a link to that video below this video in the description. In the part 1 video, I covered the troubleshooting and how I found where the first major fault was within this preamplifier. Now, there may be some other problems, I don't know yet, but that troubleshooting brings us to the first major problem that was located, so you'll definitely want to check out that video. Now, as I had mentioned in the part 1 video, there are a lot of electrolytic capacitors in this preamplifier, and all of them are going to be replaced. So you can see over here, the electrolytic capacitors have arrived, so I'll start on that replacement and going through all of those. I'm not going to show that on the video. That's not very exciting to watch, desoldering and placing components on the circuit board. But I did want to talk a little bit about selecting these capacitors, so we'll discuss that in just a moment. Now you can see the chassis is basically disassembled here. The front panel has been removed. That had to be taken off to remove the balance potentiometer, and as you'll recall in the part 1 video, that's where a problem was found. So you'll see the balance potentiometer is disassembled and it's back there, and I'll talk a little bit more about that also in just a moment. One of the first things that I did as I was starting to look over the circuit board was to start cleaning up some of the heat sinks, and on these 4 transistors right here with these little heat sinks, those have been cleaned up. Again, in part 1 there was some discussion about why that needed to be taken care of, and right back here is the next one that I'll be working on, and you can see this transistor right here, how it's clipped into that heat sink, and right there you can see that kind of corrosion that's building up on the back because of that glue, the problems. You can see the glue is just all gooped in around it there. Somewhere embedded in all that is a transistor. Now, what I found on the other ones when I started on those is that if you separate this part of the aluminum right down there, that glue just crumbles and breaks away and the transistor is left unharmed. So it's worked out okay so far on servicing the other ones. So get all that glue cleaned out of there, and then re-crimp the heatsink on with some thermal compound. And it seems to be working very well. So again, let me zoom the camera in here. You can see, go a little bit closer here. These have turned out well, and that'll definitely work better with that thermal compound under there instead of that glue. You can see that same brown glue is what they were using to hold down these capacitors, and as previously mentioned, it's becoming conductive and leads to all kinds of problems and is corrosive. So that'll all be taken care of, but those first 4 transistors worked out well. There's just 2 more remaining, the one I just showed you, and 1 more right down there. So if you're tackling a project like this that has a lot of electrolytic capacitors that need to be replaced, there's a couple things to keep in mind when choosing the replacements and kind of just going about the whole process. So as you'll notice in here, all the electrolytics now have a little black mark on top of them. That's just a Sharpie pen that I use as I go through and kind of take inventory and mark the different capacitors, as I'm counting them and looking at the values and so forth. And then it makes it really handy because as you put the new ones in, of course, they don't have a mark on them. So that's just a quick visual inspection that you didn't miss one and leave an old one on the circuit board. So there's a lot of fake components on the market, so when you're replacing any component, capacitors, transistors, whatever the case may be, make sure you're purchasing from a reputable distributor. I use Mouser and DigiKey. They're in no way a sponsor or anything of the video, but I just personally use them, and I've had very, very good luck over the years with those 2 companies. Now, the capacitors themselves, I use the Nichicon brand and also Panasonic. Again, very, very good luck over the years. In no way are they a sponsor or anything of the video. Just brands that I've had good luck with, but there are other brands that are of equally high quality. So everything over here is the Nichicon and Panasonic brand, except these red capacitors right here are Worth Electronic, and that's I believe a German company, but that was the only company that had the value for these capacitors right here that I could find with the right voltage and the capacitance value. So I've had very good luck with Worth capacitors in previous projects. It's not a brand that I think a lot of people know of, but it's carried by Mouser and other companies. So when you're replacing electrolytic capacitors, there's the electrical aspects of the capacitor that you need to be careful of when you're choosing the replacements, and also the mechanical part, the physical size and so forth. So just a couple quick tips to keep in mind. On capacitors, when you're replacing them, you need to basically stick with the original value that was chosen for a particular reason in the circuit. So if a capacitor is rated at 100 microfarad, you want to replace it with 100 microfarad. Don't go changing it up or down unless you really know about the circuit and what the effect might be. Certainly in some of the filtering circuits over here, changing the capacitor's value of capacitance could have drastic effects on the circuit. In the power supply section, if you went a little bit larger, maybe not such a big deal. Going smaller could have some poor effects on the performance. So really not good to stray too far from the capacitance value. Now the voltage rating, you never want to go lower than the voltage rating. You have to assume that it was chosen correctly, originally. So if you have a 16 volt electrolytic capacitor in the original circuit, you want to replace it with at least 16 volt, and it could certainly be higher. It could be 35 volt or maybe even 50 volt. You'll find that when you're replacing capacitors in something like this, it's 40 some years old, the new capacitors of equal specifications will be physically smaller, so you can actually get away with something that has a higher voltage rating, and it'll physically fit on the circuit board really with probably no issue whatsoever. So it's okay within reason to increase the voltage rating. Again, 16 volt, go with a 25 or 35 volt or 50 volt. That wouldn't really be a problem, but go within reason. You're not going to replace a 16 volt with something like a 250 volt or something like that, because then it does get physically much too large. Now, something else to keep in mind is the lead spacing. So a lot of these have a 5 millimeter lead spacing. That's really common. There are other lead spacings as well. But if the lead spacing is too wide or too narrow on the replacement, it won't drop down into the holes in the circuit board. You'll have the leads of the capacitor will be spread out or be pinched together, and they won't fit correctly. You want the capacitor to drop down on the board. Some of these that have an awkward tilt on them, when I replace them, they'll sit down flush on the circuit board. So we'll clean that up a little bit as well. Now, if you're replacing capacitors in a switch mode power supply, ratings like the ESR, very low ESR ratings, can be certainly beneficial and something to watch out for. In a circuit like this, really not so critical. Any new capacitor is going to have very good performance, so you don't need to be carried away with super low ESR ratings and things like that. It's certainly something to watch out for depending on the circuit, but again, any modern capacitor that you replace is kind of far outperform any of these old capacitors in here that have aged probably quite a bit. And of course, the physical height of the capacitor it has to fit within, if there's a cover coming over here, you don't want it standing up too tall. And the diameter where these are sitting next to each other, don't get carried away with something that's maybe shorter, but then it's fatter in diameter, because they may not fit on the board. So watch that. Pretty much all the manufacturers are going to give the ratings as physical sizes in millimeters. So you might find it helpful to take measurements with calipers on here and just see what those are, and have those numbers in mind when you pick out the replacements, because you'll often find the same capacitor and it'll be taller and thinner, or it'll be shorter and bigger in diameter. So lots of options and all things to keep in mind. So taking a look at the balance potentiometer, because that's where we found a problem, you can see I disassembled the original one, and right here, here's part of it. So the right channel that actually failed is this area right here, this wafer that has the resistance track on it. There's something wrong in here. The resistance track seems to have extremely high resistance everywhere, so I'm not sure if that track is damaged or what happened. Now these terminal pins were not loose. I actually loosened those up, basically intentionally trying to work some contact cleaner underneath, because I was thinking originally that maybe there was a poor connection between the pin and then the track that's on this insulating board right here. But that didn't seem to be the case. There really didn't seem to be a problem in there, and it didn't improve at all. Those could be tightened up, so I really wasn't worried about loosening those. But the problem really seems to be in this track. And oddly, there's a center track, which, let me show you this other one. This was the left channel that was working okay. And you can see the resistance tracker on the outside. So we can get that to focus there. See the resistance track on the outside, and then you can see an inner track near the hole in the center, which has no resistance to it. That's just where a second wiper runs. And again, there's no resistance on this small inside track. But on this defective portion right here, when I probe with an ohm meter down onto that track down inside there, it basically has no reading anywhere. It's almost like there's a crack or something has failed right after where the terminal crimps in right here. I'm thinking maybe there's a hairline break or something in it, because I mean, my meter will go into hundreds of megohms and it can't get any reading or any continuity whatsoever on that center track. So definitely something wrong with this potentiometer, and it unfortunately doesn't seem to be repairable. You can actually see on the, again, get this to focus here, you can see the two little wipers that are in the center right there, and then this outer wiper right there. So those center ones run on the center track, and this outer wiper runs on that larger resistance track, and then they're all tied together. You can see the metal in here. So this touches this back portion like so. This was just assembled back here like that, and then there was a metal can that was on the whole thing that crimps it together. So I had hopes that this could possibly be repaired or somehow cleaned, but that doesn't seem to be the case. Now I have located a replacement, and I'm hoping that it is correct. This is made by Alpine, has a part number on it that I am not finding anywhere, but I am finding a very similar part number, and I did find a potentiometer that looks physically the same. So hopefully it will work correctly. It has to be exactly the same to fit into the panel and on the circuit board. So it has been ordered. It's not here yet, but my hope is that it will work correctly. So when that arrives, we'll continue on with that installation and further testing and so forth on the preamplifier. Now, something else that I noticed over here was these two wires right here, just a simple issue that can be taken care of, but this is very thin wire. It's only 22 gauge. I'd like to see something a little bit heavier gauge in there, of course, within reason. 22 gauge really has no safety margin. The rating on this installation is marked as 600 volts, so no issues with that. But this wire is supposed to carry any current that would be on the switched outlets in addition to the power that's needed by this preamp, which is very minimal. The switched outlets are rated at 400 watts, and this just seems like extremely thin wire, 22 gauge for the load out here. And if you inadvertently had a fault on this switched outlets, it just seems like this wiring could basically just go up in smoke. It doesn't seem to have any reserve capacity to it. I'm really not comfortable with that thin wire that's in there, so I'll replace that as well with something a little bit more substantial. The switch on the front panel is actually rated 15 amps, so it has a nice rating well above what this would have. You're not switching 15 amps back here. So the switch didn't have any problem, but seems like the bean counters got in the way for this wiring here and went with something a little on the thin side. So you may not be familiar with exactly how a balanced potentiometer works because they don't function like a regular potentiometer. So I just want to touch on exactly how they function. You may find it useful when you're troubleshooting an audio circuit that uses a balanced potentiometer. So I have a simple schematic drawn here, and I'll zoom the camera in here and let's just take a look at this. Put this up a little bit here. Move this in like so. So you can see what I've drawn here. It doesn't really look like what you would typically see on a regular potentiometer, because you would think of a potentiometer as having a resistance track that goes from the two outer terminals and then the wiper that moves in the middle. So what's going on here? Well, let me grab this one piece right here. We can keep this in mind as well. Just set this and reposition this a little bit here. Pardon the camera movement, just kind of everything in the shot here. So this representation that I've drawn here is what's happening on these two wafers. Okay, so you have one for the right channel and one for the left channel. They're basically mirror images of each other. So you have the center terminal, which is where the wiper attaches, and then you have the two outer terminals, and you can see the resistance track that goes around. But this resistance track does not have resistance all the way around the track. It basically has resistance only halfway. Okay, so from the halfway point over to one side and from the halfway point over to the other side. So here's how it actually functions. I'm sure everyone's familiar with a balance control on a stereo or similar audio device. So you have the balance control and you've got it in the center where the detent is, and you turn it to the right side. It favors the right side, the right audio remains the same, and it's basically attenuating off the left side. And if you have it on the center detent and you turn it to the left side, then the right side is being attenuated and it's favoring the left side. But you're not actually amplifying the side that you remain to hear, it's just attenuating the other channel. And that's actually what you can see is happening here. So the two wipers are ganged together, of course, and in the center position, there's absolutely no resistance through the balance potentiometer. So you have the center wiper comes up and then it comes over to the other side. So basically looking here, the right audio comes in here and then the left audio comes in here. All right. Then the other side, as we saw in the schematic, it's tied to ground, so that resistance track, and then it goes to ground, all right? Now, what happens if you, let's say you turn it to the right channel? So both of these wipers, again, they move together. So on this side here, the right audio is coming in and it had no resistance, it was going right out. And if you turn it all the way to the right side, this wiper moves all the way over. Again, no resistance, audio is coming in on the right channel, going out the wiper, no change. But over here, it's now added resistance. In fact, if you turn it all the way over, it's shorting the wiper to ground, and you would have no audio because your left channel comes in here and the wiper is over here, so the wiper's at ground potential. Nothing comes out of the wiper terminal on the left channel, and that's exactly what you would want because you've turned it all the way over to the right side. And then the opposite happens if you go to the left side. This wiper travels all the way over to this side here. Left audio is coming in, going right out again to the wiper terminal. And on this side, this wiper is now moved all the way over to the ground potential. And if you stop somewhere in the middle, maybe it's halfway in the resistance, and then you would have attenuated audio, but some would still pass through. So the right audio is coming in here, going through some or all the resistance, and some or no audio is coming out of the wiper terminal. So it definitely functions a little bit different than a traditional potentiometer that has a continuous resistance track. Really important to keep in mind how this actually functions if you're troubleshooting one of these potentiometers, and very important to keep in mind how this functions if you're replacing one of these potentiometers. If you put a standard potentiometer in place of this, even if it has a center detent like you might find in some potentiometers for bass and treble controls, it will not work correctly because you'll have resistance on this side as well. You'd have resistance over here, and then that would attenuate the audio, and again, it wouldn't function the way it's supposed to. All right, I'll continue on with some of the capacitor replacements, or I should say all of the capacitor replacements. And when I have an update, I will be back, and hopefully that potentiometer arrives soon. It actually has to come from an overseas vendor. I could not find it in the US, unfortunately, but it does appear to be a genuine Alps potentiometer. I was pleased about that. So it should be good quality, but it is coming from an overseas vendor. So it may take a little bit time to get here, but when it's here, I'll get it installed and we'll continue on with the repairs and troubleshooting. I now have all the electrolytic capacitors replaced, and you can see the pile of old capacitors back there. Definitely quite a few of them. So as I was removing each of the old capacitors, I tested them, and I found that many of them had a high ESR value, and some of them had excessive leakage current, but pretty much to be expected given the age of the preamplifier. So if you're not familiar with the term ESR, it stands for equivalent series resistance, and the ESR is basically the resistance that the capacitor exhibits that's in series with its own capacitance. And you do want a low value. So just to give an example, some of the old capacitors were measuring around 12 to 14 ohms of ESR when the new capacitor was measuring 1 ohm or less. So quite a difference. So I'm sure that the performance of the preamp would be degraded by those old capacitors because none of them tested all that well. So I'm very happy with the way the circuit board turned out at this point. It looks a lot better because just getting all those capacitors replaced, the new capacitors are positioned, neatly and standing upright on the circuit board, where many of the original old capacitors were tipped and leaning at odd angles, so it just gives a better appearance on the board. And I spent some time cleaning up the board, getting the glue off in this area here. There's a lot of glue in this back corner. You can see on these capacitors. None of them were leaking, so that's not leakage that you see on there. That's that old glue. It becomes corrosive and conductive. So definitely good to get all of that cleaned up, taken care of. Now, the transistors that are on the board that have these little heat sinks clipped to them, I removed each of those heat sinks, added some thermal compound under the heat sink, re-crimped it onto the transistor, so those will be working very well at this point, dissipating the heat much better, because originally this just had some glue under those heat sinks. That's really not appropriate at all. And these heat sinks right here with those power transistors, I put some new thermal compound on those. The original heat sink grease or thermal compound was very dry and crusty on those, so it wouldn't be doing much either. And the remaining components that were on the circuit board, some of the transistors and other capacitors, I cleaned them up, repositioned them a little bit. Some of them were leaning over, again, kind of odd angles, and some of these capacitors that are kind of a clear color, particularly back here in the phono section, were standing way up off the board. Some of them were almost a ½ inch up off the board, and that can lead to hum and other problems in the circuit. I'm not sure why they positioned them so excessively high off the board, but that's all been taken care of at this point. So again, very happy with how the circuit board has turned out. Now the next thing that I will do on the board itself is to clean up these switches, the main selector switches right here, these selector switches in the front, these two potentiometers right here, and I'll just use a cleaner like this, This is an electronics cleaner with the lubrication in it. You always want to use a cleaner that has a lube in it, because if you use just a standard electronics cleaner with no lubrication on a potentiometer, it can make it very, very dry, and they'll wear out very quickly because the wiper will just basically wear away the resistance track, and switches will end up pretty much hanging up because they're so dry that the little mechanism inside the switch, when you press the switch and turn it on and off like that, won't work correctly if you stripped it away, you know, and just used a cleaner that has no lubrication. So just something to keep in mind when you're servicing and cleaning these. And back here, this wiring they had looped around in a little bit different manner, and I've repositioned it here because it was running very close to this part of the circuitry over here, basically touching up against these the backside of these jacks right here, and this is where the audio goes out, so the preamp out right here. The last thing that you want to do is introduce 60 hertz hum or 60 cycle hum into the audio. So I wanted to get this wiring away from this portion right here, so I've tucked it back into this corner right here. So that should work very well. And then this wiring right here, the two original wires that I mentioned were only 22 gauge, very light duty wiring. I've replaced with this 18 gauge wire. I feel a little bit better about that. If there would ever be a fault on something that's plugged into the back of the preamp, that 22 gauge wiring just didn't seem like it would ever handle any kind of an overload condition. And again, the switch on the front panel up here is rated 15 amps, so it wouldn't have any issue, but this wiring will be a little bit safer. And this is rated 600 volt insulation, which is the same as the original insulation. So the potentiometer has arrived, and you can see it here. However, there is an issue with it. Grab the original one here, and that is that the shaft is unfortunately just a little bit too long, but it's better that the shaft be too long than too short, because I should be able to shorten the shaft up a little bit, just cut it. So you can see the original potentiometer here. I've disassembled it, so the back part is missing. It originally looked like this, of course. And you can see the new potentiometer, the shaft length is just a little bit too long. However, the good news is that the back side of the spline part of the shaft is the same length right here. And there's a part that's not splined, and then it goes into the threaded portion right here where the mounting nut goes on. And if you look, that part is the same distance out. Okay, so that's all the same. It's just that the splines extend a little bit further on the new one compared to the old one. So it mounts to the circuit board with no issue, and then when it is mounted on the circuit board, I just stuck it into the position right here. The center line through the shaft is the same as these other two potentiometers right here. So I don't see any issue with it other than just the shaft length being too long. Of course, it is a balanced potentiometer. It has the center detent and electrically works correctly. So I'll go ahead and shorten up the shaft a little bit, and then I will return with the potentiometer installed, and we'll try out the preamplifier and see how it's functioning. I cut down the shaft on the new potentiometer, you can see right here. So it very closely matches the original potentiometer. So let's get it installed and try out the preamp. I have the new potentiometer in position, and you can see the mounting nut is installed, but it's not actually soldered to the circuit board yet. And it's important to do it in this order, because if you solder the potentiometer to the circuit board first, and then the position of the potentiometer is tilted up or down a little bit, or maybe left or right or something like that, and then you put this mounting nut in position, there could be a lot of tension on the potentiometer, and it could possibly break the housing or crack a solder or something like that. So you always want to mount it first and then make the solder connection. So if I turn this a little bit like so, you can see the potentiometer is just sitting on the circuit board right there, and then the 6 legs of the potentiometer poke through to the bottom side of the board. And I'll go ahead and get those soldered now, and then there won't be any strain or tension on that potentiometer. Okay, I have the ADCOM GFP-1A front panel reassembled, as you see it here. I'm very happy the way that turned out. This is the balanced potentiometer that was replaced, where the shaft was cut a little bit shorter, and you can see the knob fit very nicely on there. It's even on the front with all the other knobs, so it looks very nice. And I have the bottom cover left off in case there's any more troubleshooting, just to access the bottom of the circuit board. Now the first thing that I want to do is measure the power supply voltages, just with all the work that was done in here, all the replacement capacitors, just to make sure that the voltages look correct. And if they do, then we'll move on to testing the audio sections, and we'll use the oscilloscope for that. But first we'll start with the digital multimeter, take a voltage reading. So let me grab my power cord here and get this plugged into the isolation transformer. All right. So let's see what happens. Transformer is on, yep. Here we go. Alright, looks okay. We have a power indicator light here. There's not any kind of excessive power draw, so that looks good on the isolation transformer. Reach across here and grab these test leads. So The negative lead just goes to the chassis for ground reference. I'll just poke that in there. So the unregulated side is on these heat sinks here. So we have, yep, 46, almost 47, like it was before, so that looks fine. 47.7, no problems there, that's the negative rail. And then the regulated side right here is on the emitter. All right, negative 34.9, so right at negative 35. That looks very good. And the emitter on this one, back in here. And there it is, 35.2. No problems with that, looks very good. So power supply voltages are looking fine. So I think it's safe to move on to testing the audio sections. So I'll work through the various controls and the selector switches that are on the front panel and just make sure that everything is functioning correctly, and we'll see how the different controls affect the audio waveform, and we'll take a look at that on the oscilloscope. Let me reposition things. I'll get that digital multimeter moved out of the way so that there's a better view of that oscilloscope display. Okay, I have things repositioned on the bench so that you can see the overall setup a little bit better. So, moment of truth. Let's see if the preamp is functioning correctly, or do I have some more work to do? So for this setup, I have my signal generator connected to the tuner input on the preamp, but it could also be on the tape input or the digital audio disc input. It really wouldn't matter. Now, the phono inputs are a much lower level audio signal, and we'll look at the phono section a little bit later on, along with that CX noise reduction. And then the output of the preamp is routed over here to the oscilloscope. So the left channel is on channel 1 and the right channel is on channel 2. So this is channel 1 right here, and then this is channel 2 down here. So what we're looking for is an equal sine wave on both channels. So we want to see equal amplitude. We don't want to see any clipping or distortion. And again, it should be the same level on both channels, except when the balance control is rotated, which is where we ran into trouble originally. Okay, let me switch on the signal generator. All right, it's turned on. So the signal generator is at 1 kilohertz at 250 millivolts RMS. 1 kilohertz is a very common frequency for testing audio equipment, but I'll vary that frequency as we work through some of these controls that are frequency dependent, like bass and treble. And the 250 millivolts RMS is just a low level that's perfectly fine to use something above or below that. Within reason, you don't want to overdrive the inputs on the preamp. Okay, so signal generator is turned on. Let's see what happens. Increase the volume here. Hey, look at that. Looks like it's working. We have a signal on both channels. So let me reach over here and just make an adjustment on this. So volume control is working very nicely, no problem there. So just stopping at that point right there, we have equal deflection. You can see the amplitude on the sine wave is equal on both channels. So the deflection is 2 gradicules on both. So very good, no problem whatsoever. Let's increase this. I'll just change this here. Got one more. Let's go all the way up on the volume. Oh yeah, there's a lot of amplification there. Yeah, look at that. That's 5 volts per division. And there's absolutely no clipping or distortion, and the volume control is at 100%. So that looks really good. No problem whatsoever. Let's just take a quick look at the balance control. Oh yeah, look at that, no problem there. So that's favoring over to the right channel. And again, this is the right channel, so perfect. That's the center, and that's favoring to the left channel. Oh, that's outstanding. That looks really good. Very happy with that. So let's put the volume back about in the midpoint here. A little bit more deflection, about like so. So yeah, that looks really nice. No issue whatsoever with that. So let's work through some of these controls and see if they're working correctly. Now, before I put this front panel on here, I did measure the resistance on the bass and treble potentiometers, and I didn't see any issue with those, so I felt that I could reassemble this and not have to, get back into here to do any more work with any of the controls that were on the front panel. So the bass, I believe, is right here. Yep, this is the bass control. So that's going to be a much lower frequency. We're at 1 kilohertz right now, and rotating this, actually I need to switch that in right there. Yeah, see, there's really not any effect at the 1 kilohertz. That's perfectly normal. So I'm going to lower this down all the way down to 100 hertz. Okay, and make a adjustment right there. So that's 100 hertz right now. So let's take a look at the bass control. Oh yeah, no problem there. So that's turning the bass all the way down, back to the midpoint there. No problem whatsoever with that. Let's go up to say 10 kilohertz here. So 10 kilohertz and adjustment over here. Okay, so that's 10 kilohertz now. Let's take a look at the treble. Oh yeah, no problem whatsoever there. Both channels change in unison, and we have a nice amount of cut or boost. No problem whatsoever with that. Again, balance control is looking very good. So there are two filters right here. The first filter says 20 hertz, and then the other filter is 25 kilohertz, okay? So the 20 hertz is actually going to be a high-pass filter. What that's actually doing is cutting off frequencies below 20 hertz. So let's see how effective that filter is. So let's go back to, let's say, 100 hertz. Okay, there's 100 hertz right now. So not really any change at that point when I switch that filter in, so that's reasonable. It's not really doing anything. So now let's go down a little bit further. Go to, okay, there's 20 hertz. That's probably the best I could do on the trace. Sorry about the flicker on the scope there, but you can still see that waveform. So we're at 20 hertz right now. If I switch this in, yep, we do have some attenuation. And then let's go a little bit lower. Let's go down here to 10 hertz. So that's a 10 hertz signal. Oh yeah, and 10 hertz really attenuates very sharply at that point. So there the filter is out or off, and there it's on. You can see it's all practically a flat line, just a little bit of a wiggle there. So no issues with that filter. That's working very well. Let's take a look at the 25 kilohertz filter. So the 25 kilohertz filter is actually a low-pass filter because it's passing frequencies below 25 kilohertz and cutting things off that would be above that frequency. So I'll go here to, let's try 20 kilohertz. Throughout all of these frequencies, you can see that the deflection is basically remaining at 2 radicules as I'm changing the frequency, which means that the response of the amplifier is very flat, and that's what we want to see. That looks very good. So let's engage this 25 kilohertz filter. A little bit of attenuation, not a lot. So 20 kilohertz is the upper end of the audio, frequencies that you would expect. So it would be normal that there wouldn't be a lot of attenuation right there. But let's go a little bit higher. We're to 25 kilohertz there. Oh, yep, there's more. And let's just continue up here. You can see that waveform's getting pretty small at that point. That's actually 50 kilohertz right there. Yeah, this preamp has a very wide frequency response because with that filter out, you can see the response. It's still about 2 radicules of deflection at 50 kilohertz. And that's with that filter engaged. So it seems to be working fine, no issues with that. So let's take a look at the loudness control. So first of all, let's go down, turn that down a little bit. Let's go down to, let's say, 100 hertz. Okay, we're at 100 hertz on there. Lower this back down. Things just adjusted a little bit better here. So I actually do want to put that down there. Pardon all these adjustments here while I get things set up. Try that. So the volume control is positioned at a lower level here. That's something that would be a softer, level if you were playing music or some actual audio that you were listening to. Let's engage the loudness control, and you can see that it starts to boost it right there a little bit. Let's go up a little bit further. Yep, no more noticeable even right there. So you can see the loudness is off, and then when I turn it on, the signal gets a little bit larger. Oh yeah, big difference right there, you can see. Now let's try, go over here. Yep, and that's normal. So when you can see the volume control is turned up, if this was playing music through an amplifier and you were listening to the volume at this point, that would be extremely loud on most setups. Most amplifiers would really be driven pretty hard once the volume is turned up here to this halfway point. And at that point, the loudness control doesn't really have much effect. You can see turning it on and off right now. Some effect, but not a whole lot. If I go a little bit more. Not much at all right there, and you can see that right now, let's see, the detent is right about there, so a little past that halfway point right there. Okay, so again, turning the loudness on and off doesn't do a whole lot at that point, and again, that's perfectly normal. That's how the loudness is supposed to work. So very happy with the performance. That's looking very good. I don't see any issues whatsoever with the controls across the front panel. But the last thing to do is take a look at the phono section and also the CX noise reduction. As you recall, I mentioned in the part 1 video, CX noise reduction is basically an obsolete noise reduction that was used on vinyl records. So it only affects the Phono 2 selection on here. So let's see if the CX noise reduction is actually functioning, and there's a calibration procedure. So I'll take a closer look at that. I'll explain about that. This came with a test record, which I also mentioned in the part 1 video. Of course, I don't have that test record, but that was a way that any user could have set this up back in the day. But again, it can be done with a 1 kilohertz tone, so we'll take a closer look at that. There's some indicator lights on the back panel, and that'll give an idea if this part of the circuit is actually functioning. Be interesting to know if that's actually working or not, even though it's not really usable, because finding records that are encoded with the CX noise reduction is pretty rare at this point. But for nostalgia's sake, it'd be nice just to know if that is actually working. So I'll reposition things a little bit here, and we'll take a look at that. So something that I want to clarify, in the previous part of the video, I was using 250 millivolts RMS from my signal generator. However, the technical specifications for this preamp are listed at 150 millivolts RMS sensitivity for the digital audio disc input, the tuner, and the tape inputs. But it's okay to deviate from that 150 millivolt RMS level unless you're trying to run tests on the preamp and compare exactly to factory specifications. You might want to pay closer attention to that signal level value. But for the type of test we're running here, it's absolutely fine to deviate from that. It's not an issue whatsoever. You just don't want to go to an extremely small signal level. It would just make measurements difficult, and you don't want to go to something so large that you're causing clipping and distortion, or if it was an extremely large signal, it might even damage the input circuitry within the preamp. So keep that in mind. But again, the 250 millivolt RMS level, and even something maybe larger than that, 300 millivolts RMS, not an issue whatsoever, would not cause any problems. So moving along to the Phono preamp sections. So again, there's a preamplifier section within the preamp for the Phono sections, and phonographs or record players have very, very low output levels from their cartridges, and they need a lot of amplification even within the preamp, and that's what this part of the circuitry over here is doing. There's also some specific equalization that occurs over here, and that's a whole other topic to get into, but the signal level over here that I'll be using now from the signal generator is set at just 2 millivolts RMS, so very, very low level. Now this is an earth ground right here, and you'll see the effect when I remove this, but there's a lot of hum and noise on the bench. There's fluorescent lighting, there's a computer nearby, and switch mode power supplies and things like that. And there's no shielding on this because the top and bottom covers are removed, and there's metal covers would offer a lot of shielding on this circuitry. So you'll see a little bit of a jitter and noise on the waveform, but again, perfectly normal given the situation that the preamp is in over here. So I'll connect this over here. We'll start on Phono number 1 on the left channel. And we do have a nice sine wave there. So again, we have a 1 kilohertz signal, and it's at 2 millivolts RMS. And this sine wave looks very, very good over here. No issues with that. Rotate the volume control. No problems there. Now if I remove the ground connection, you can see a lot of noise right there. Just removing that earth ground. That back again there. Definitely helps to quiet the signal down a little bit. So there's a sensitivity switch right here for Phono input number 1, and it's 2.5 millivolts or half millivolt, depending on the cartridge that you might have in the record player or the phonograph. So if I switch this over to half millivolt, you can see a lot of gain there, and that looks very good. I switch that down No problems with that. Waveform looks very good. Sine wave looks great. Switch that back. Let's take a look at the other channel. So again, phono number 1, but we'll move over to the right channel. It looks very good. Same amount of vertical deflection, so we have equal amplification on both left and right channels. Switch that over. That looks very good. We take a look like that. Yep, no problems there. A lot of amplification on the higher sensitivity setting, so no problems. So let's take a look at phono number 2 with the CX noise reduction turned off right now. Let's see, we'll go right here, start with that. Go back to the left channel here. And switch this, put right there. All right, no problems there. Rotate the volume a little bit. Yep, looks good. Move this over to the other channel. Let's take a look here. Also looks very good. No issues with that. Again, same amount of amplification occurring on both channels because the vertical deflection, the amplitude of the signal is the same. So let's take a look at the CX noise reduction and see if that part of the circuitry is working correctly. So as I mentioned in the part 1 video, this preamp was originally issued with a test record to help you calibrate it, but you don't need that test record. All you need is a 1 kilohertz signal at 4 millivolts RMS. So let me increase this up here to 4 millivolts so we can see a much larger signal there. Just turn this down like so, like that. And let me switch in the noise reduction. Oh yeah, that makes definitely a difference there. And we can see the light change back here, the little LED. It says over right now. So what we're going to do is there's a left and right adjustment potentiometers here, and you do one channel at a time, so just one input, and then you make an adjustment so that both indicator lights have turned off. All right, so I'm going to grab my test tool here, or my little adjustment tool, and because we are on, let's see, this is the right channel, we want to go over here, and let's rotate that. Oh yeah, that's making definitely a difference on the amplitude on the signal there, and we can see the light changed over here as I was lowering that. Yeah, right there, it looks like they want to toggle between one and then the other. It looks pretty good right there. So the green LED is just trying to turn on, the red one has turned off, so that's probably about where that should be set. Right about there. Very reasonable, looks good. Both of those lights have turned off. Let's go over here to the other input. And let's make an adjustment here. So this is the left channel now. Yep, makes a difference on the level of the signal there. See if we can get both of those lights to turn off. Yep, right there. It looks like they're kind of toggling right between the two. Pretty sensitive. There we go. Yeah, we can see that the amplitude of that signal is the same as it was on the right channel. The number of gradicules of deflection vertically is the same. So we can get that other. There it goes. It's right there. It's just, I think the green LED was just starting to glow just a little bit, but very, very close there. Basically turned off at this point. So it looks like the CX noise reduction circuit is functioning, even though it's not something we can really use. It's just nice to know that it does actually function within the preamplifier. And there's one more test we don't want to forget about. That is the headphone amplifier. So this preamplifier has a dedicated headphone amp, and that section is right here. So we want to make sure that that amplifier is functioning the way that it's supposed to, and that both left and right channels have an equal amplitude signal with no distortion or any problems. So let me grab the scope probe right here, and I'll clip the ground onto the chassis, like so. So I'm inputting a 1 kilohertz signal right here on the left and right channels on the tape 1 input, okay? And I'll just probe right here onto the circuit board. So I believe that is the right channel. Looks very good, no problems with that. Very good looking sine wave. So we have 2 graticules of deflection above the ground reference point. So let's check the other channel, and yep, again from ground reference point, 2 graticules of deflection above and below ground. So the amplification is equal on both channels, no problems whatsoever. The ADCOM GFP-1A is now completely reassembled and it's ready to put back into service. I'm definitely looking forward to getting many years of use out of this preamp. So I hope you enjoyed following along with the troubleshooting and the restoration that went into this preamplifier. And if you did enjoy the video, please remember to give it a thumbs up. And if you enjoyed this video and the other videos on this channel, please remember to subscribe. There'll be many more videos like this coming in the near future. So until next time, take care. Goodbye for now.